Hi, I'm Soumyendu Sarkar from Hewlett Packard Labs, and I'll be presenting some of the work that we're doing on quantifying and measuring robustness of machine learning models and how to refine these models to enhance robustness. Now, machine learning models have a peculiar vulnerability where a small perturbation of data may cause a model to misclassify for image classification. Such perturbations occur naturally at deployment because of distortions from camera like dust, sensor decay, or fogging. It can also occur from adversarial attacks. Now, also, we were looking at how to measure and quantify robustness. We anticipate stricter regulations of like machine learning usage, as we are seeing in the EU and now in the US, which will require algorithmic audit and measurement of trustworthiness. Now, one of the key limitations on how machine learning models are tested today is the static nature of the tests. We rely mostly on the static data to evaluate the models. As we were looking at this complexity of machine learning models, we thought, why not leverage machine learning to test the trustworthiness of the machine learning models? Now, here, as you can see, let's see how it works, right? So here there is a beer glass, cannot be any clearer, and should not be hard to classify it. Right? As you can see, the distortions, is successively added on the bottom left pane, and the classification probability changes, and soon the machine learning model with a very little distortion that you see being added on the top on the bottom left, it misclassifies it as a gas station. So this is one of the main problems that we are addressing. Now, a robustness for the machine learning model is key for ensuring consistent classification accuracy with variations in input data, and is an important element of trustworthiness. We wanted the agent to work with black box models, which is of advantage as we do not need access to the model code, and also it needs much less specialized data scientists' efforts, so that we can democratize measurement of robustness. Now, to tackle the complexity of the machine learning models, we used some smart machine learning technology called reinforcement learning to evaluate these robustness and to find out the minimum distortion needed for the misclassification. Now, unlike many other adversarial attack techniques of today, we keep these distortions limited to the Gaussian noise to keep it close to the naturally occurring distortions that we see today. Now, this will also lower the risk of for the users in deploying the underperforming machine learning models to increase the return of investment, decrease liability, and help in regulatory compliance. Now, this provides also the quantitative metric for robustness and can also be used for algorithmic audit for trustworthiness. In addition, this technique can help retrain machine learning models to enhance robustness against outliers, as we'll soon see. So how it works is here we have got a smart agent, and as you can see, we evaluate so the smart agent adds distortions to the images, and then it passes through the image classification model to see what is the effect of those distortions. Now, but we are using the smartness of the machine learning agents to add the distortions at specific areas which are the vulnerability of the machine learning models. And what we are also doing is, as we're analyzing the specific vulnerability of the machine learning models, we are creating new synthetic data, which we call adversarial samples. And these adversarial samples kind of encapsulates the vulnerability, and then we are going on the outer loop to retrain the machine learning models so some of those vulnerabilities gets fixed, and the machine learning model becomes much more robust. This is typically, in deployment, what happens is you have lot of unseen data and test data which are coming in. And whenever we detect some of the vulnerabilities, we generate this adversarial data and we train against those vulnerabilities, which is called adversarial training, to fix those robustness issues. Now, let's see what happens, without retraining the machine learning model. Now, here, as you can see on the bottom left, there's very little distortion that is needed for the classification flip to occur. Now, after the first retraining, when we had made the machine learning model robust enough, now we need more distortions for this cougar to change into the wildcat. And after secondary training, we need even more distortions to be added for the misclassification to happen. As you see, it's pretty resistant to the noise, and then the cougar face, which is this class, it stays on for a long time before it switches to the wildcat. Now, if we recapitulate, what we're doing is the original image has no distortion, and then after for the untrained model, like we see with a little distortion, we get the flip. Then after we do the first retraining, it needs much more distortion to cause the flip, and then it needs even more distortion after the second retraining. Now, this process cannot go on forever, but in the initial few retrainings, we see quite a bit of increase of robustness. Now, one thing to note is here, we are not changing the model structure. We are not even analyze, trying to re-architect the model structure. We are instead, I'd say, enriching the data which encapsulates the vulnerability of the model and training them for the good. So let's also look at some of the other sort of distortions. So the earlier distortions are all based on noise, right? Gaussian noise, which is natural occurring noise. But we can also extend this to dead pixels. So if you see, this is a picture of a bulbul now, and if you look at it, there are tiny spots which comes up over here, just like the dead pixel in the image sensors, which cause such vulnerabilities for the model to flip. Also, we can do blurs, which is a typical effect of blurring on your image sensor lens. And as you can see, there is a tiny blur which appears over here. And if you look at the original image is clear, and this tiny blur at a very, I'd say, vulnerable area of the image can cause it to misclassify. This is another, this is a sea anemone. And again, look, it's similar to human perception. When we look at it, we look at the finer details. And now track, the blur is a tiny blur at the center, which is kind of how we humans think. So these are some of the data augmentation techniques by which you now change the static nature of the test data to a hacker who dynamically can morph the test data to find out the vulnerabilities, to quantify how robust a machine learning model is, and then we are using this adversarial data which we have generated to train the machine learning model to make it more robust. Now I'll hand it over to my colleague Liam, who is now implementing it in a way this computation scales. And HP has got this.
Hi everyone, I'm Liam, and I'm excited to show you how you can apply what Soumyendu just showed you to, using our open source library called Determined. And Determined is basically a platform that focuses on making model development at scale easy and highly usable for groups and teams of ML developers. So, on day one, if you're a single ML developer, you're working generally with small experiments on single GPUs, and therefore you don't really need a lot of the infrastructure That's really useful when you start scaling to more GPUs or when you start requiring kind of guarantees around reproducibility and being able to collaborate with your team and so on. So Determined is a platform that focuses on the day two of machine learning development, where you want to have infrastructure that can help you manage multiple GPUs and perform more complicated machine learning workflows like hyperparameter search, and also track all of your experiments so they are reproducible and shareable across your group. Another thing that we help with is distributed training, which can be hard to configure and fragile to use, especially if you're starting from scratch in the cloud or on your own on-premises machines. Some of the main features of Determined are kind of shown here, and we'll get to see a few of these components in the demo. But as I said before, Determined really focuses on the model development portion of the ML development pipeline. We integrate with solutions kind of before and after training. So, we integrate with various data storage solutions like S3 and bucket storage in the cloud. And then we also work well with kind of downstream applications like Selden and MLflow that kind of make serving much easier. But the core of Determined is really focused on training, and you can see some of the features that we support here. And I think many of these features help tremendously with usability and being productive, especially as you start scaling to more GPUs or just larger data sets and so on. So let's see how we can use Determined to use the robust adversarial data generation method that Soumyendu presented previously. So here we're looking at the Determined web UI, and right now I'm using Determined to run a cluster on Google Cloud. And you can see there are various buttons over here on the left side that kind of summarize various things that you've done on your cluster. I'm going to go over here in the tasks and open kind of a notebook that I've set up previously to do adversarial example generation. It's this one. So you can see like Determined, you can work with notebooks and Determined very easily. It's hooked up to a shared file system that we've created in the cloud. And I just have the R lab, which is the technique that was presented before. I have a demo up here to kind of show how you can very easily use this just in a notebook. So doing a bunch of imports over here and configuring how we want to generate the data. Next, I'm just going to create the data loader and also the classifier that we're going to attack with the method. So now you can see the classifier has been loaded. We have the data. We're going to get one data example here and then ask our lab to basically generate the adversarial image iteratively by successively adding natural noise, as we saw in the presentation. So it looks like in this case, we finished very quickly in just 3 iterations. So I'm guessing this image was not particularly robust. So this is the CIFAR 10 data set. So unfortunately, the resolution here is pretty low, so 32 by 32. But as you can see from the result, we start with an airplane. And by adding a small amount of noise just in the corner there, it suddenly flipped the prediction from airplane to frog. So a notebook is all nice and good when you just want to interact with your data and maybe get a feel for how an adversarial attack performs. But once you're at a stage where you want to apply adversarial generation to a large data set, that can be difficult to scale if you don't have kind of the machinery and setup to provision GPUs and schedule multiple GPUs to run generation for you. And that is kind of where Determined can help a lot with the workflow. So I have an example here that basically runs that exact process that we just went through in the notebook, but now I can throw as many GPUs at the problem as I want. So this is kind of very similar things that we looked at in the notebook. Have a function to help us visualize the results that will be put it to TensorBoard. And as you can see here, it's very similar. Load the data, get the classifier, and loops through the data loader now to generate all of the examples. With Determined, scaling from just one GPU to multiple GPUs is as easy as changing a single line in an experiment config. So if we start with the single GPU example, have hyperparameters that kind of control how the images are generated. And as part of the resources, I'm telling Determined that I want to use one GPU here. And if we look at a multi-GPU configuration, everything is the same, except I just changed the slots per trial under resources to 4 or whatever number you want to use. So with that configuration, I can now create an experiment in Determined. So I'll launch both a single GPU and a multi-GPU experiment. And we can come back to the web UI to see what's happening on the experiment end. So I've created a workspace and a project to kind of aggregate all of these experiments together since they're related. And I want to be able to see all the experiments I've run related to this question in one place. So the 2 experiments we just created show up here in the web UI. And if we look at this current experiment, nothing is being generated because in the background, we're actually provisioning instances in Google Cloud for you. So this is why this hasn't gotten started yet. And similar thing is happening with the multi-GPU experiment. But I do have a few experiments that I kicked off a little bit before that we can look at to see kind of what the model development process looks like with Determined. So let's look at this completed one. So this is the multi-GPU experiment, and you can see like I've registered basically the average L2 distance that quantifies model robustness to this kind of Gaussian noise. That's all being kind of tracked over here as part of the experiment overview, and can see the robustness of the model for the CIFAR10 test data set is around an average L2 distance of 2.2 that's needed to basically flip a class label. So this is all being tracked and determined. You can see this. You can see the hyperparameters that were being used. The logs also show up in this panel here. And you can filter by rank. Since we used 4 GPUs here, you can see, you can basically filter to the logs that are being generated by each individual GPU. And we can also open up a TensorBoard to look at the various images that were being generated as part of the adversarial attack process. So right now the TensorBoard is spinning up and it's copying data from Google's cloud bucket, where we basically persisted the TensorBoard events automatically for you. So I know I might have generated quite a few images, so that's probably why this is taking so long. But we can come back to this in a little bit. Let's take a look now at what's going on with the other experiments that we submitted. So we can see now the cluster usage is higher because we've spun up additional GPUs. And right now we're just setting up and launching the individual processes to generate the examples. So let's wait a little bit more for this TensorBoard. You can see so we're scheduling a TensorBoard. That's why we're spinning up a CPU instance to handle the request of basically handle the request to render the TensorBoard events and spin up the TensorBoard service. So the TensorBoard service is finally up in one of our CPU instances, and you can see with Determine, we're actually also automatically saving a bunch of basically the same time series, but in a more granular fashion to TensorBoard. I've also outputted images periodically so that we can see what the original versus adversarial examples look like. So you can see we're basically spitting out these images for visual inspection and fixed intervals. And this one. So this one we can see was actually fairly hard to flip because we had to add a lot of noise like so much so that it's like visually noticeable with the human eye. This one, not so much. As you can see, like going from automobile to truck, and intuitively those two are much closer. So we didn't have to add as much noise to flip the label. So I think that's the TensorBoard integration with our product is also very useful to help you track the examples as you generate them. So now the examples that I'm generating are all being saved into shared storage. So this is one of the folders with the adversarial examples. And for retraining, we can basically point the model retraining code to this shared file system to train with adversarial examples. And again, take advantage of things like distributed training to speed up that process as well. So that concludes my demo. If you're interested in learning more about our product, as I said, it's fully open source. So you can go check us out on GitHub and get started locally with your local cluster to see just whether it would help you with the day-to-day work that you're doing in machine learning. Thanks so much for your time, and it's a pleasure to be here at the Data-Centric AI Summit.